we're looking at a highly unusual event in space exploration today. I mean, this started as a totally routine launch, but it ended with a spectacular, totally unplanned collision on the lunar surface. We're going to track the entire life cycle of this piece of hardware, the intense scramble by global space agencies to watch it crash, and the incredible geological secrets it ended up revealing. So, you're probably wondering, what actually happens when 4 tons of solid metal slam into the moon? To really appreciate the scale of this event, we have to talk about the sheer size of what hit it. We're talking about the second stage of a SpaceX Falcon 9 rocket. This isn't some tiny piece of satellite debris. It is roughly the size of a 5-story building, weighing in at a massive 4 tons. Now just imagine that sheer mass floating through the silent vacuum of space, completely dead, devoid of fuel, totally beyond human control, and heading directly for the moon. It sets the stage for a truly unprecedented astronomical event.
Pot 1. A surprise lunar collision. The Falcon 9 crash.
5,400 miles per hour. That translates to roughly 8,690 kilometers per hour. That is the astonishing velocity at which this 4-ton rocket stage was traveling when it finally slammed into the moon. Tracking data confirmed it struck near the Einstein Crater, right over on the moon's western limb. And because the moon has absolutely no atmosphere to slow incoming objects down through friction, this rocket stage hit the ground with the full, unmitigated kinetic energy of its incredible speed. Well, the immediate physical aftermath of all that kinetic energy was, frankly, violent. The sheer force of the impact blasted a brand new crater into the lunar surface. Scientists estimate it's about 60 feet wide and 12 feet deep. But it wasn't just a dent in the ground, right? The violence of the crash instantly vaporized material and threw an enormous amount of lunar dust and shattered rock, which we call ejecta, outward for miles, creating this massive plume rising high above the moon's surface. Now, what's really interesting here is how it even got there in the first place. Part 2. How did it happen? Tracing the trajectory. Let's wind the clock back and trace the timeline. It all started back in January of 2025. SpaceX launched a Falcon 9 rocket carrying 2 commercial lunar landers, and that included Firefly Aerospace's Blue Ghost. Now, usually rocket upper stages use their leftover fuel to intentionally fall back and burn up safely in Earth's atmosphere. But this specific mission required extra thrust and velocity to get those landers all the way out to the moon. Once it pushed its payload, the second stage literally lacked the fuel to steer itself back. So for 18 months, it just drifted aimlessly. It took an impromptu, totally uncontrolled tour of the Earth-Moon system as a giant piece of space debris until its final crash in August 2026. But why the moon? Well, as Juliana Scheiman, SpaceX's director of NASA Science and Dragon programs, explained, this was actually just a product of natural cosmic forces. Over that year and a half, the dead rocket was constantly being nudged. Think of it kind of like a very slow game of cosmic pinball. A combination of the gravitational pulls from both the Earth and the moon, mixed with solar activity physically pushing against the object, slowly altered its trajectory. Nobody aimed it at the moon. Rather, the complex orbital mechanics of our solar system just mathematically guided it there. This event, naturally, sparked a pretty big conversation within the astronomical community. Bill Gray, the astronomer whose software first tracked the object's path, noted that while the crash presented absolutely zero danger to anyone here on Earth, it does highlight an ongoing debate about space junk, and what some view as a certain carelessness regarding how leftover space hardware is disposed of. As Earth's orbit gets more and more crowded, managing these dead satellites and rocket stages is a highly discussed and sometimes debated topic. To provide the complete picture here, we also have to look at NASA's official stance on the matter. They note that while this specific Falcon 9 impact was completely unintentional, disposing of upper stages by actually crashing them into the lunar surface is a technically accepted and safe method. In fact, for certain missions in low lunar orbit, it can literally be the only practical option. It provides a predictable end-of-life outcome rather than just leaving dangerous debris floating around in orbit. Part 3. The global observation effort, a coordinated effort. Tracking this thing was an incredibly international effort. Because the impact was predicted to happen on the far edge of the moon, making it notoriously difficult to see from Earth, global space agencies really had to scramble and leverage their best assets. We had the European Southern Observatory pointing their massive, very large telescope from the ground in Chile. Up in space, NASA positioned their Lunar Reconnaissance Orbiter to sweep the area, and absolutely crucial to this whole operation was South Korea's KARI agency, utilizing their Danuri lunar orbiter. And the Danuri orbiter, it truly delivered. South Korean scientists initiated active orbit control of Danuri about 30 minutes before the collision even happened. They secured 8 distinct imaging sessions, passing right over the site multiple times. They captured the pristine lunar terrain just before the crash, and then the immediate, raw aftermath. I mean, this before and after footage was absolute gold for the scientists, allowing them to confirm the exact changes in the terrain and carefully map out how all that ejecta spread. So, the crucial point we're getting to is part 4, the accidental science opportunity, an unplanned experiment. The mechanics of how astronomers actually captured the data from this were just brilliant. You see, the impact happened right near the moon's terminator, and that's the sharp boundary line separating the sunlit side from the dark side. So step 1, the rocket hits. Step 2, the massive dust plume is thrown violently upward. But because of its location right at the terminator, that plume suddenly caught the sunlight against the pitch-black background of space. Step 3, while the plume was glowing in the sunlight for just a brief 5 to 10 minutes, telescopes down on Earth used spectroscopy to analyze the light and actually determine the exact chemical makeup of the dust. The spectroscopic data they gathered from Chile was fascinating. The analysis revealed 2 distinct gas signatures, sodium and lithium. Researchers quickly deduced that the sodium came from the moon itself. It was vaporized lunar regolith blasted out from deep beneath the surface. The lithium, on the other hand, well, that was an artificial signature. It was a trace material originating from the vaporized Falcon 9 rocket stage itself. By separating the two, scientists essentially got a free, deep-core sample of the moon's crust in that highly specific region. Now, to put all of this incredible data into some proper context, while a human-made object hitting the moon feels super dramatic to us, to the moon, it's basically just another Tuesday. Because it completely lacks a protective atmosphere, it takes a beating. A natural meteoroid carrying the exact same kinetic energy as that 4-ton rocket hits the moon roughly once every 6 days. The moon absorbs this kind of force all the time. The real difference here, this time we knew exactly when and where to look. Which brings us to our final thought. We gained invaluable data on how impact plumes behave and how ejecta actually settles in lunar gravity, all from this one accidental crash. As humanity gears up to return to the moon through the Artemis missions and eventually build permanent lunar bases, understanding the mechanics of how the lunar surface reacts to high-velocity impacts is going to be absolutely crucial for safe landing and construction. So, how will the data from this wild accidental experiment shape the blueprints of our future lunar outposts? It is a fascinating question, and one that scientists are going to be studying for years to come.